Sorry, my screen's black now. Okay, no, it's not dead. Okay, I think we just have to start here. I don't know if the camera will work, and if not, like it doesn't seem to be my computer's issue. It's great to see you all in person. The first thing I want to say is that we'll probably be able to shut down the Thursday session. The Thursday session was because on Tuesday, we would otherwise have more people than the room fills. At least for the time being, the number of people showing up here Tuesday and Thursday combined is less than all seats taken. So we'll probably be compacting things. We'll have to see how that goes, and we'll be emailing you, of course. I don't think there's a final answer, but like from my look, it's like a lot of people just prefer tuning in online. What else should I say? Okay, cool. Let's jump right in. Let's talk a little bit about admin. And after talking about admin, we should very, very briefly review what you learned with the second set of notebooks. And then we'll have some question and answers. And then I want to spend a lot of time giving you an idea of the overall gestalt of the field. So my friend Dorbold built this amazing visualization of all the important, many frequently cited papers of the deep learning field. We will go through them. And the hope is that you have an idea afterwards what these many subdisciplines of deep learning are. And that directly fits into the course going forward, which is you will then, after seeing the overall gestalt, you'll be able to see what we teach, how that fits into it. And for the projects that are coming, you will have a little bit of an inspiration. Okay, what are these clusters? What kind of deep learning papers do you find interesting? And therefore, what kind of projects could be interesting for you? So in that way, we'll talk about the deep learning field overall, the history of that field, how that field got where it is, and why it works the way it does. The next thing I want to encourage all of you, sometimes I hear from you, that was a really crappy description of things. And yes, sometimes the way I describe stuff isn't great. And sometimes any one of you will have a better idea of describing it. Now, as you know, all our materials are on GitHub. Because they're all on GitHub, every one of you can just put in pull requests. I love if people tell me, your teaching is not good. You could do better. Here's how you could do better. Put in pull requests. We will make sure to get you extra points for doing that. And you will feel a certain ownership for the course. And the course it's a non-standard format. I also want to briefly say something about the non-standard format. A few of you are now at this stage where it's like, it's kind of weird. This is not the course like the way most courses run. It's different. And it's different on purpose. What we find and what the past literature finds is that in the standard way of like, professor gives some talk, you go home, do homework, that format doesn't often lead to people actually being able to use the skills. That's why we have this somewhat weird format where you just have one lecture a week, and then we will mostly focus on the notebooks. Then you have your group, your pod to talk about them and make sure that you learn the things that you wanted to learn. It's weird on a lot of people early on. By the end of the course, a lot of people will like it. So what else? Briefly mentioned permits. By now, everyone should have their permits for real. Has everyone gotten their permits? Anyone still need permits? Okay, if anyone still has like admin problems there, email Anka. We should have that all under control by now. And to everyone, I also want to, of course, apologize. Sorry it took so long. We didn't intend to make two courses out of the one course, and that's where all that administrative problem came from. But a lot of you told us that the courses were important for you. So we really making an effort to allow as many of you as wanted to enroll in the course. At discussion, the invite should be coming or already came. I think it's already on Slack. You wanted a place that's more like Piazza. Your pen is migrating from at discussion to Piazza. No, from Piazza to at discussion. And that's why we'll be using Piazza for that. That allows a good tracking, and we can make sure that all answers are given by the TAs. Personally, I still prefer Slack because Slack is kind of what real-world teams use. And for me, in this course, the projects are really, really important. For the projects, you will need more like the kind of mode of discussion that you have in Slack, because you'll get together with groups. At first, you will message with others, hey, I have this idea, I want to do this project together. And if you will later on do startups or something, you will find yourself in that same space where you'll be using Slack all the time. And I think it's really useful for that. Great. That's all that I have on admin stuff for today. Any questions on the admin side? Okay, cool. Let's move right on. Let's briefly review what we've seen this week. We have seen automatic differentiation, and we used this compute graph. And I apologize that a lot of people were confused deeply by the compute graph. What does the compute graph mean? So in graphical models, an error means that a variable depends on the things that you have arrows going in. So it clearly means that here, C must be a function of A and W2, for example. As we assume that things are linear, there's two possibilities, which is either either it could be W2A, matrix multiplication, or it could alternatively have been the scalar product of those two. Some of you did it one way, some of you did it the other way. That's totally the same thing. And we will, of course, get all the points, and we didn't spot that there's two ways of interpreting it. It also teaches you another thing, the danger of symmetric matrices. No? If we had taken 2x4 matrices for one and like a 2x2 matrix going in or something, the problem never would have occurred. In any case, apologies for that. Now let's talk a little about what this one means. Now, like B analogously is W1A or scalar product W1. Or like pointwise product, W1A. And I believe it was originally meant to be the pointwise product. Same thing for D. No, D is then W4C plus W3B. And L mean squared error between the output of that and a constant that's repeated 9 times, 3 by 3. Then automatic differentiation, same thing going back. Now, like the derivative of the loss after D is then just 2 times the product there. And then it goes into those two chains. Now we calculate the derivative of the loss after D. Then we calculate the derivative of the loss after C by multiplying the derivative of D after C with the derivative of L after D. Same thing for B, same thing for A, all goes back together. Now, it's like the usual. You probably have seen that in 519 or 520. Just once you have the compute tree, compute forward, gradient descent backwards. Now, let's make sure that we all understand what this means. How much slower is it to calculate the gradients as it is to calculate the loss? Is it like O of n slower or something? What would happen? And I do need a different mask, and I apologize. I will be like cleaning my glasses many, many times via lecture. Okay, how fast is calculating the gradient relative to the loss? Well, that's like super important. Like if gradient calculations are expensive, and I can do things by forward calculation, I want to avoid it. If gradients are cheap, I want to always use gradients for anything. So how long does it take in a compute graph to calculate L versus DL after all the others? Yes. Okay, let's think about it. On the forward pass here, let's say we have matrix product here. We have C is W2 times A. Now, what is the derivative of A after C? Now, what are we doing? Is there an inverse matrix? We have to invert W2. Now, this is vanilla gradient descent. This is not a trick question. So what's the derivative of A after C? Hold on. Derivative of, oh, this is correct. No, like this is here, let's see. Imagine it was a scalar. What we'd have is W2. Now, if it was just a scalar. What is it if it's a matrix? No, it's not 1 over W2, it's W2. Not like just the derivative of this after this. This thing goes away, leaves just W2. Now, am I confused? C A this way. Okay, cool. BC over DA, it would be W2. What if this is not a scale? It will be transposed. No? Now, if I want to calculate the derivative of the loss after A, I need to multiply the derivative of the loss after C times the derivative of C after A, which is this term. Okay, so how much longer does this take me? Now, like here, if I want to calculate the derivative of the loss after A, and imagine, ignore the other chain. Now, like, okay, we can write it. It's not like just through the C chain is DL over DC, DC over DA. Okay, this is what we already calculated before. This is something that we have. The vector of the length of the vector that we have in C. Okay, so in that sense, this thing is just a matrix multiplication. Okay, it's the same one. It's on the way forward, we multiply with matrices. On the way back, we multiply with the transpose of the matrix. Okay, therefore, the backwards propagation takes exactly as long as the forward calculation, apart from maybe somewhere where we deal with nonlinearities. So we effectively, practically get the derivatives for free because we need the same number of multiplications to go back than it takes us to go forward. So gradients are super cheap. This is why we use gradients whenever we can. Okay, and this is an intuition that is really important for you to have. It means that we can solve. That's the reason why neural networks are so good. You know, like we basically get, if we have n weights, we get that whole computation, the whole gradient computation with O of n. Every weight, I need to do a multiplication on the way forward. I need to do a multiplication on the way back. And therefore, we use it all the time. Great. And that's the whole reason why the field of neural networks is successful. Okay, we briefly talked about linear regression. The interesting thing in linear regression is that we can do this transformation. And a lot of people have issues with the interpretation of that. If we have a multi-layer neural network, okay, I can always say we have then y, the output vector. And the loss would be a function of the output vector in this way of drawing. The output vector is the input vector here times W1. That's what happens in the transition to the first layer, times W2 times W3, and so forth up to Wn. I can rewrite this as V times X. I can do singular value decomposition of V. That then gives me that I can write the whole thing as a rotation going into the network, a multiplication with just a diagonal matrix, and then a multiplication, and then a rotation on the way out. I don't care about the input out. What I care about is the dynamics. Once we have that there, we have lots of weights and sequence. If I multiply lots of weights that are drawn randomly, some of them will have very small products. Some of them will have very large products. That then translates to some of them basically being initialized with very small values, some of them with large values. On top of it, some of them will be strongly correlated to the error, and some of them will be weakly correlated to the error. The ones with the strong correlation to the error will learn faster than the weakly correlated. This is what gives rise to these dynamics, where we can say the overall error here stays almost constant for a long time. Why does it stay constant? Why would it stay constant for a long time? And you see that often when you train neural networks, right? that they maybe there's some initial learning and then they stay for a long time. And you will see, all of you will see that for a lot of networks that you'll be training. Network goes, stays there, nothing happens, and then it gets better. Why is that happening? Yes. That's right. So what we do with neural networks, we initialize the weights to be very small. And we have this long chain. So the gradients will be very small because it goes to many small steps, if you want. Because the gradients are small, at first nothing happens. And all the neurons in that chain will be learning in parallel, will learn at the same time. And they will all be learning, and they will go up exponentially, in fact. But they start at 0. And then exponentially, that starts at 0, stays at 0 for a long time, until it hits the region where it's no longer 0. And then it can go very fast. And this is what this analysis of Sachs shows. Start at large errors, and then the first component kicks in, gets us better. The second component kicks us in, more components kick in, and so on and so forth. And they kick in one after the other. And this is very typical when you train neural networks, that it's not the way you might expect, that it just goes down and goes to 0. Instead, it kind of messes around, nothing much happening, and then it gets much better. Messes around, then it doesn't get much better. The cool thing about this paper by Sachs and Ganguly is that it allows us to understand in that linear approximation why this is happening. Why is this happening? You have these small components that are there and sleeping that don't do anything. Because they don't do anything, their gradient is 0, or very close to 0. Because their gradient is very close to 0, they don't learn. And it's kind of this like bootstrapping that then gives rise to this very, very fast kicking in. And this is what you see there. Now, you can rightfully say, but Conrad, like, look, this is linear learning. Linear learning is the most boring thing. This is not what we are interested in. But it turns out, that. Okay, cool. No, but it turns out that even networks that are not linear, that are nonlinear, they inherit all those properties from the linear networks. And in general, as we build more and more complex models in deep learning, we build them out of components that we understand that are smaller. This component of linear learning is in every network that ever exists. And it's the only domain, or it's one of the main domains where we can really make nice theoretical statements. It's a domain where we can really have an intuition of why things work. And this intuition is what I wanted to give you. So basically, if we have shallow networks, they will generally learn like this. If we have deep networks, even deep linear networks, they will generally have this property where they like are somewhere and then they go down and then they go down and so forth. And that is because the relevant spectrum just has like some large associated products of the many layers and some small. Okay, we also talked about some about cost function engineering in the things. You saw the mean squared error, mean absolute error. Why would we, and I know like for a lot of you this is just a repetition, but under which circumstances would we want to use the mean squared error? Yes. If they are relevant or if they're irrelevant? If they're relevant. Okay, so if we have, so I want to push you a little on how you think about outliers. So outliers is actually very complicated. Where do outliers typically come from? Yes, many of them come from error in measurement. Let me give you an example. I might be a company. I might be checking how much people are willing to pay for my product. I ask you how much you're willing to pay. I'm like, tell me in dollars how much you're willing to pay. And you're like, $5, $4.99. And he writes $599. He meant $5.99 and didn't add the comma to it, or the point, as you do in America. In that case, we might want to ignore him. In fact, ideally, we'd fix the data point that's there. In that case, the outlier comes from not the data distribution, so I want to ignore it. And in that case, what kind of an objective function would I want to use if I want to ignore the outliers? Mean absolute error, exactly. Why? Because the derivative of the cost function is effectively the weight that you put on things. If I have mean squared error, the importance on data points is the derivative of this, which is linear, which means that the further away you're from the mean of the distribution, the more weight you have. In the case of the absolute error, which looks like this, I should have used multiple colors. These have negative weights, and then these have positive weights. It basically means that everything just has a vote on how we want to estimate something. And everything has the same amount of a vote. Why do we often want to use mean squared error instead of mean absolute error? Like mean absolute error gets rid of outliers, and like most real world data sets have outliers. Anything I can think of, almost anything I can think of has like outliers, labeling errors, all those things. Why do we often use mean squared error? Yeah. Mean squared error is always differentiable, but in the context of deep learning, it's not much of a problem because the probability that you end up on zero, like if every neuron has a bias and it has a slope or it has a weight vector, the probability that you end up on exactly zero is of course arbitrarily small, at least if you randomly initialize. But but in that so therefore the probability that you hit that one place, like absolute error is differentiable everywhere apart from zero. So therefore, usually you don't hit it. But the real reason why you often use mean squared error is statistically you have more power, because if you want, you can use all the data. If you assume that, say, the data is drawn from a Gaussian, and many real-world data sets are, it just means that to reach the same statistical power, you will need less data points. So in that sense, there's a trade-off between these two. We can also use the number of correct guesses. But now, here's a question that I want you to ask, and I want you all to think about it. What's the right loss function? And there is an answer to that. What is the right loss function when we optimize something, when we do a machine learning project? Now, what's the right loss function? I'm a company. I produce something. You work for my company as a data scientist. I ask you, tell me what you predict that person's going to pay for my product, say. What's the right loss function? Who gives you the loss function? Where's loss functions coming from? Now, the real world is not a Kaggle competition. In a Kaggle competition, someone says, the model that, do you all know Kaggle? Okay, cool. In a Kaggle competition, it says the team that has the smallest mean squared error wins, or the team that maximizes the percent of correctly recognized elements wins. In the real world, no one hands you that. But let's first talk about Kaggle, because that's something we can all agree. Imagine you have a competition that says percent correct is what determines who wins. What do you want to optimize? Well, you want to optimize percent correct. If you optimize something else, it won't be so good. Now, in lots of cases, here's a problem. Percent correct is, of course, not even differentiable. On top of it, percent correct might not give you as much data than mean squared errors for something. So what you often do when you want to win those things is you first train your system with a loss function that is good for giving a lot of data for your algorithm. And then you took the output of your machine learning algorithm and you train that output to optimize the correct cost function. Maybe the percent of correctly recognized things. So it's the world that gives us the loss function that we really want to optimize for. We can use all kinds of tricks that maximize the data that the amount of data and the power that we have and so forth. But we, in the end, want to optimize what's right. Now let's go back to the pricing case. What does your company want to optimize? Now, so concrete case, get lots of data of customers, how they interacted with our webpage, what they bought. And I want you to tell me how much I should charge him. He just came to our webpage. He built some algorithm. It needs to give a dollar number, and I'll be like, you can have it for X dollars or not. Then you go away. What cost function would we want to use in that case? Yes. Profit, exactly. Optimize for what matters. If you're in medicine, optimize for quality adjusted life years. If you're in whichever domain you're in, optimize whatever it is that actually matters for the specific case. And this is the biggest problems of data scientists. The problem, if you're out in the real world doing science or engineering, in academia or industry, the problem isn't that you don't have the right tools. You're going to get the right tools in this course and other courses. The problem is that people see these prompts, they recognize, oh yeah, there's a network. Let me download that. The network that you download has a certain cost function. This cost function is not what your domain requires you to optimize in none of the areas. So the important place for us data scientists to think is, what are the real cost functions? What is it that we should be optimizing for? And that is where the typical project falls short. Cool. What else? Intricacies of network optimization, initialization. You saw Xavier and he, and the most important thing is I think you saw the principles behind it. Now, what are the goals of weight initialization? Well, I want like the forward calculation to give me something, not just zero output, and I want the gradients to not be vanishing. I also don't want them to be exploding. And then we navigate that terrain. That's what he and Xavier said. So before going to questions and answers, and I should have brought some water, I want to see if you have the right intuitions. Now, you all took machine learning courses before. Almost all of machine learning happens in high-dimensional spaces. Now, weight vectors might be million-dimensional in deep learning. So they're in very high-dimensional spaces. So what we're going to draw is we're going to draw an n-dimensional Gaussian, where on every axis we have zero mean and we have sigma standard deviation. And we're in an n-dimensional space. So what's the angle between two vectors in such a high-dimensional space? Or what's the distribution of angles in such high-dimensional spaces? Let's say n is really big, like bigger than 100 or something. Yeah. Yes, the angle. Ah, that's great. Yes, we can. We have vector x that we draw from this high-dimensional space, and we do a scalar product with that. And now, if we take this, and we divide it with the norm of x. Okay, let's start with x. xy is the length of x times the length of y times the cosine of alpha between us. Okay. Now we can of course calculate this. No, like cosine of it means that cosine of alpha is xy over x y. Again, now what's the angle? Yes. The arc cosine of that? Sure. But, and we could do that if you give me x and y. But what I'm telling you is in high dimensional spaces, I don't need to give you x or y. They're both drawn from that probability distribution. Yes, in high dimensional spaces, vectors drawn like this are always perpendicular. Why? X and y. This is the sum of xi, like here. Y is sum over I of xi yi. Now xi yi, they're all drawn from this 0 sigma. Therefore, the expected value here, the expected value of xi yi is 0, of course. And then the expected value of xi yi squared is some kind of a constant, and it depends just on the sigma. Okay, each of them, so the variance of each of these terms is a constant. The mean is 0. If I have n of those, I have n times the constant. Now, in this case, we have, instead of n times, we have n squared. No, because it's always the same. They have not, they don't, the vectors are always multiplied with itself. Now, like here we have xi yi. In that other case, we have xi squared. Xi squared is always greater than 0. Okay. What that means is that this ratio here is going towards 0 as n gets to be large, which means that high-dimensional vectors are always orthogonal. Now, why does that matter in neural networks? Okay, I learned something. I have a vector, maybe at the second layer here. Okay, here I have an input layer. Here I have a hidden layer. X, I have a hidden layer of an output layer. Okay. I now do one step of learning here. So we have here, W is W plus, W1 says W0 plus delta W, where this is the gradient. Okay. And then I have here, I have a vector that differs, or like another matrix W2 that we use for reading out. And say we have one vector to say, is this likely to be a dog? And another vector that's likely to be a cat. As long as there's no structure being introduced by learning, the weight change that I have on one thing, maybe I just learned that this is a cat, will be orthogonal to whatever I use to recognize that it's a dog. So that means that in a way, in those high-dimensional spaces, learning doesn't catastrophically interfere with other things. Because in high-dimensional spaces, things are always orthogonal to one another. So the gradient that I impose on this, the way how I change the hidden layer, will not massively change if I now want to do something else. And that is the reason why neural networks don't do really bad things that you would have if they were small, a low-dimensional set. It's also the reason why if you look at deep learning as the field, it's always better to make it bigger. And like, why do we use GPUs? Because using big neural networks is better than using small neural networks. What's the advantage of high-dimensional spaces? It makes these kinds of interactions be smaller. Now, I want to skip over the others. It's time for some Q&As. But the reason why I wanted to briefly talk about high-dimensional spaces is in this week, in the linear learning week, is where you started being exposed to computational, to theoretical principles. We saw how we can understand learning in linear systems. And the intuition for high-dimensional spaces, you've probably seen in previous courses. The question is what it means. And deep learning is explicitly using these like high-dimensional intuitions in lots of ways. And that's why I thought that this is a part that the professors might have skipped over before, but that will, as you keep doing deep learning, will give you a lot of insights about it. They're like, what does that mean? If I want the learning of one thing to not destroy the learning of another thing, well, then let's embed them in a high-dimensional space. Let's make the layers large, because then we will have less interference than if they're small, because all vectors become orthogonal. So, any questions? Yes. Okay. I was thinking of like questions about the last week's materials, but like, yes, this hidden layer has a certain number of neurons. When I initialize, I will have a random projection into that space. I choose how many neurons I have here. In many cases, I might have an intuition that a problem is low dimensional. Not like there's rumors that say even ImageNet is just like 30-dimensional. There's a manifold somewhere in space. And yet the winning competition elements, they all use networks basically as big as you can fit into a GPU. Why? The reason why big compute translates into good performance is by making your systems bigger. You can minimize like the kinds of interference that you don't want to have. Any questions for the week 2? The reason why week 2 is so important to me is because this is where you get exposed for the first time to theoretical concepts, to things that, in my view, produce meaningful intuitions on what will work and what will not work.
Is there like a probabilistic like sort of paper that goes into that actual effects on N?
Yes, wonderful, great question. There is this concept that's called the neural tangent kernel. I think one of the videos mentions it, but like we don't have much space for neural tangent kernels. So neural tangent kernels is a way of quantifying, of thinking about neural networks as kernel machines. The idea is the following. The most natural way of thinking about learning is that I can say, I learn one thing, or like all my data points, they lie somewhere in a space. If they lie close to one another in a space, then they're probably the same thing. They should have the same label. They have the same regression output. If they're close, if they're far away, they should have different ones. in kernel machines, you basically build all of machine learning around this concept. Neural tangent kernels are a mathematically beautiful way of showing that under certain circumstances, neural networks just operate as if they were kernel machines. Specifically, in the examples that you have, in the SAX kind of situation, you initialize the weights very small, and then they exponentially go up, and they produce the dynamics as we've seen before. If you initialize them with large weights, then you're in the so-called kernel regime. In the kernel regime, you can think of learning as basically every data point influencing all other data points according to a kernel that defines how they're similar. And neural tangent kernels are one of the standard ideas of how we can really understand learning in certain classes of neural networks. Great. Yes.
In practice, people do study the singular values of weight. Is that just not the next singular value?
So singular values are they're an up-and-coming technique in neural network where people like Guillaume Lahoye are building like really beautiful computational frameworks around it. They characterize the dimensionality of the computation that you do. And thereby, now you can say in the extreme case, you have a few non-zero singular values and all the other singular values is zero. It means that any learning happening in the future in the linear case will only relate to the first one. Now, if we go to the nonlinear case, it will act like a linear case apart from correction factors. These correction factors can, in a way, put variance into dimensions that are otherwise zero. They don't always do that. In practice, if you look at gradient descent, you calculate the SVD spectrum of the gradients of, say, a bunch of subsequent mini batches, it is a relatively low dimensional phenomenon as well. Singular values is just a way for us to discover these things. So looking at the singular value spectrum is a way for us to get some insights into why learning might fail. It also gives us some insights into, if you want, the inductive biases that we have. Now, like you all probably know Wolpert and McCready. No free lunch theorems? Who knows NFL? Like the statistics of. Okay. NFL is arguably the most important foundational aspect of machine learning, more on the theory side. Now, like I should say one more thing. We will now heavily go into you implement neural networks and build them. But right in the beginning, we wanted to have theory there. No free lunch theorem says that no learning algorithm is any better than any other learning algorithm. Why? So it's a constructive proof that says for every problem for which one algorithm is better than another. Now, let's say I do linear regression, you do convnets. For any problem that you're better than me, I can construct your problem for which my algorithm is better than yours. And the way to interpret NFL is that basically the reason why algorithms work better than others is because they know something about the world in which we are. The things that we know about the world in which we are is points that are close in space tend to be similar to one another. That's what's called an inductive bias. And we have lots of them. Us humans have lots of them. For example, things that you see right now in this world are probably still there the next moment. We have inductive biases that say the interpretation don't change much over time. If you later go to self-supervised learning, which is a big topic in deep learning at the moment, it's all based on such assumptions that you basically say, the interpretation of the world doesn't change much. If I have text, it's repetitive in a way. There's all kinds of ideas, or like you can say a good model is one that allows me to guess like things that I've seen before. all kinds of things like that. But NFL is basically the reason why we should think about deep learning in terms of inductive bias. What we build into our networks are beliefs about the world. ConvNets work the way ConvNets work because we believe that the world is translation invariant. We believe that things appear in all kinds of configurations that gives rise to, or we believe that we live in a world where there's a small number of important things that gives rise to transformers. And NFL sets the background of that. So a good number of people basically teach machine learning courses starting with NFL, which is basically learning is impossible unless you already know something about the world. And cool. Any other questions? No, we should move on. So what will you learn this week about? It's optimization week. Using good optimization algorithms is always necessary to make real-world neural networks work. There's a lot of tricks, and you will learn lots of them. Stochastic gradient descent, batch normalization, momentum, rate scheduling, adaptive learning rate very fast. Those are all the pieces that we build optimizations out of. And it's not just about finding a minimum. So oftentimes when people start thinking about optimization for neural networks, they're like, optimization is finding that good point. It's finding the point where you fit the data really well. That's not the main goal of optimization in machine learning. What we want in machine learning is that it works well for the data that we trained on, and that it generalizes on test data that we didn't train on. And it turns out that the way we do optimization for deep learning has lots of little things that make things generalize better. If anything, the way we practically regularize in deep learning is by the way we design the optimization process. So we're not trying to get an algorithm that, like, say, brings us to the best solution as fast as possible. We try to find an algorithm that generalizes well, and that changes the whole way of thinking about it. Specifically, among other things, it means that we don't just want a minimum that is deep, but we also want one that is shallow, where basically small changes in the parameters don't destroy many things. And we will talk about problems, not like what happens if there's no gradients, what happens if they become too large, what if they lie in a low-dimensional space, which comes back to like why SVD is an important way of thinking about these things. But now I want to do something that is much more fun that I think will be really useful for you. I also found that while Zoom is running, while these things are stuck into my computer, everything's a little slow. Good. Yes. This. Okay, so maybe first the history. So I was running this thing in summer that teaches a lot of students about deep learning. And I found it hard for me to visualize, to explain to people what's the gestalt of the field. Now, there's so many deep learning papers. What's different? What are the classes of things? And in response to the discussion that I had with Hendrik, he built this thing. And what we see here is all the heavily cited papers at the conference called NeurIPS. I've been going to NeurIPS since 1999, I believe. NeurIPS back then was a small conference, some 800 people. Now it's a huge conference with more than 8,000 people, and publishing in NeurIPS is about as hard as publishing in Nature. Back then, that was very different. Even people like me could publish it. So every single thing here is a paper. And the size of it is how many citations it gets. Color-coded is which year it's from. You see, like 1959 are the oldest papers there. Yellow, light yellow are the newest papers. So let's look at a few areas. So this cluster here is something that is not part of this course, or at least not to a significant part. These papers are all really old school neural networks. Let's look at a few of them. Neural networks, the comprehensive foundation from 94. here, identification and control of dynamical system using neural networks. So all those papers were like in the 90s when neural networks were super uncool, people were doing things with neural networks. They weren't using many of the modern methods. And back then, they were still very much interested in neuroscience. So a lot of these papers have like some real crossover. They wanted to describe brains. Weirdly, if we go back into the history of neural networks, it was not to build self-driving cars. It was to understand brains. And then over time, we get towards computational applications. So this is a first method. This is like old school neural networks. Beautiful work, not used much anymore these days. So let's zoom into what we have below here. Here we have then, no, let's have that later. Let's look at this cluster here. This cluster here is old school vision research. And I should say in all those areas, there still exist new papers, like old school neural networks. There's still people asking, how can humans memorize things? How does the monkey decide how to move the hand or something? So that all still exists. Similarly, the old questions of computer vision still exist. I give you an image. Can you draw in every pixel that belongs to content? It's still a real problem. They were building these things a long time ago. Let's look at a few classical papers here. Eigenfaces for recognition. This guy in 91 took a large data set of human faces and just ran PCA on it. And the first, and so you have the average face, and then you have the first difference against it, which might be skin tone. Some people have darker skin, some have lighter skins. And then the second principal component might be some people have longer faces versus shallower faces, and so on and so forth. In 91, it was very cool. And I remember reading that as a young PhD student, and I thought it was very amazing. Rapid object detection using a boosted cascade of simple features. Nice set of tricks. Totally get the job done in 2001. Here, an iterative image registration technique with an application to stereo vision. Why image registration? If I want to use stereo vision to see how far away you are, I have to align what I see on each eye and find the same point as seen from one eye and seen from the other eye. That's not entirely trivial because the world from one eye just looks different as the world from the other eye, and there's some noise and so forth. And so this is old school vision. Good. So these are the things that we won't cover. Here, also in this area is like old school machine learning. A lot of the things that you've seen in previous machine learning courses fall into this. Now, like here we have libSVM. Who has used libSVM before? Okay, it's like a super fast package to run support vector machine. It's still being used. Here we have like random forest. Who has used the random forest in this room? Oh, I thought everyone. Okay, almost everyone. Yes, you used it. Leo Breiman, 2004. Standard citation for that. Here, programs for machine learning. Scikit-learn. Who's been using Scikit-learn? Ah, yeah, it's my favorite. Okay, so this is, if you want, old school machine learning. And with old school, it doesn't mean it's no longer useful. These techniques are still state of the art for lots of applications of machine learning. But it's not neural networks. Cool. So, and we will not be covering this. Basically, old school machine learning, that's your past courses. And here, there's no reason to learn about old school neural networks. We do deep learning. There's a whole bunch of tricks that we newly have that weren't there. Now let's go through the other areas. What do we have done there? This is an area of basically, now you see wireless learning architecture, network surveys, communication. This is kind of all the non-standard applications of machine learning, like machine learning for communication, machine learning for swarm robotics, machine learning in all for power grids. Like this is a strong embedded, make it well work in the real world thing. And you can see they're very different from all the others. They're also quite similar to old school machine learning. Why? These guys solve problems. These guys discovered ways of solving problems with machine learning. Still exists. Let's look at this cluster here. This is reinforcement learning. Now, this course has, so in the first couple of weeks, you learn the basics. You need them because you can't build neural networks unless you're like really firm on the basics. Afterwards, there's 3 areas that we will spend significant time on: computer vision first, convnets. Then we will spend some serious time on natural language processing, including recurrent neural networks, LSTMs, things like that. And then we will talk about reinforcement learning. And then at the end, we will basically be at the level where we are in research, which is the alpha 0 level, where we can solve like real things like chess or Go with like with deeper reinforcement learning. In that area, the foundational book is Sutton and Barter 2005. And you can see the gradient. The new stuff is like on this side. Human level control through deep reinforcement learning, Demis Hassabis. This is, I believe, the Atari paper. So this is like these guys basically, DeepMind in London, having, I believe, 400 million invested in them by Google, basically going after one target in reinforcement learning, and they did many of them. They have the best chess playing thing, they have the best Go playing things, they do AlphaFold, where they do protein folding and so forth. So we see this gradient here. Now, Sutton and Barter laid out the rules. Now, deep down, reinforcement learning has never really changed. Deep learning is just a drop-in to solve 2 problems of it. What are the 2 central problems in reinforcement learning? It's how should I explore the world around me? Should I try this or should I try this? That's one part, the exploration strategy. The other part is, do I think it's better for me to go there to solve the problem or to go there? And for that, I need some evaluation. Like, is it better if I have a queen or if I have 2 rooks? Like that kind of question we want to answer with it. So in reinforcement learning, we basically had the same ideas that Sutton and Barter set up. And now we replace these things that they use basically with hacks with deep learning, which is another way of solving the same problems. Okay, that is the cluster that does reinforcement learning. This cluster, as you can see, lives kind of far away from all the others. Why? For a lot of the other techniques, they go like into directions of self-supervised learning. There's a lot that text has in common with vision. So these fields always inspire one another. Reinforcement learning is a very peculiar situation. I interact with the world. I give the world actions. The world gives me values back. And I'm trying to become successful in that world. It's a very peculiar setting. And that's why that field is very far away from the others. Now, they use a lot of tricks from the others, but there's no strong affinity with any one other group. So this is going to be what we'll do towards the end of the course. Then let's look at the other factors. So here we have graph neural networks. We will not really cover graph neural networks. Some of you will find graph neural networks super interesting. You can do that as project. Graph neural networks are in a way just convolutions on just stuff that has the shape of a graph. And the question is, if many of you will never experience a graph problem that you need to solve. And that's why we didn't want to make it a central part of the course. They exist as areas. If you're into social relations, say, everything is a graph problem. But for a lot of you, graph problems will just not appear. So then we have this big cluster here. Let's look at the key paper here. This is Schmidt-Huber's long short-term memory. So maybe I should give you a little bit of the history because it's quite interesting. So most famous in deep learning are the 3 people who popularized it. Who popularized deep learning?
Yes, Jan LeCun.
Jan LeCun, absolutely. In fact, Jan LeCun did deep learning 16 years or 20 years before everyone else did deep learning. He built these things to solving MNIST very efficiently. Yeah, so Jan LeCun was one of the 3 people. And so Jan did that at a time when it was super uncool. And then there's two other names associated with it. Jeff Hinton, who's an emeritus in Toronto, and Joshua Benger, who is working at Montreal. And we're collaborating on a few things. So in any case, long short-term memory here. All these are natural language processing papers. Why is LSTM the key paper in natural language processing?
Because I guess it enabled you to sort of like information from farther back.
Yes, exactly. So long short-term memory is a trick of taking a memory about something and keeping it until you make decisions based on it. The way that trick works is it basically is a piece in a neural network that says, store it now, and then like don't do anything with it. No, read it. And then makes it much easier to propagate the gradients, and we'll talk about that extensively in recurrent neural network days. Why is that so important for text? The reason why that's so important for text is if I ask you, say, a question answering thing, I'm like, neural networks like contain lots of nodes. Now, what defines neural network? And here will be lots of nodes. Then that kind of relevant piece might have come a long time before the time when I ask you that question. So you need some way of managing memory. Transformers are equally in this thing here. Let me see. Well, I can't find it. But like transformers are basically built on the idea of RNNs. They just do it in a way that is much more efficiently trainable. But they're in a way similar, only that they don't just say keep the memory, but they're like, instead of keep the memory, now look there. And by telling the network now look there, it's as if it has memory. I basically show the whole path to it and allow the network to choose what it wants. In that way, it does something very similar to LSTM. So here we have all the NLP papers. As part of NLP, we will, of course, cover recurrent neural networks. We will cover transformers. We will cover about how to convert words into a format that you can do meaningful things with. And then we have here, this is the arguably, look here, you see the biggest papers. Here, what do we have here? Deep residual learning. This is the ResNet paper. ResNets is a trick to make vision networks work really well. It's a trick where you take every layer's output, the layer's output, and you basically let every layer just do a difference operation on it. Therefore, gradients don't vanish. Gradient vanishing is the real problem when training neural networks, so everyone uses it. Here, very deep convnets for large-scale image recognition. That's 2014. That was like the second paper, like the paper that improved over AlexNet. Let's see if I can find AlexNet. Here we have AlexNet. In fact, we have 2 copies of AlexNet for reasons that I don't understand. So AlexNet 2012 was the revolution that made deep learning all of a sudden be a thing. Pre-AlexNet, you tell people, oh, I work on neural networks. They're like, oh, it's so sad that you don't have the math skills necessary to do support vector machines. Post 2012, it was like, oh my God, you do deep learning. I want to do that too. So this is the papers that are roughly in this cluster are all like computer vision, like make things like object recognition work. Algorithms that tell me this is a hand, this is a cat, that's a dog. That's kind of all that is happening in this relatively narrow cluster here. Great, what else do we have here? Now we have a cluster here. That's all GANs or GAN-related things. So GAN, the idea of GANs is a neural network tells me if this is a cat. Now I want to invert that. I'm like, okay, draw me a cat. And the way GANs work is you basically have an artist that draws an image. And you have a faker detector, which says like, no, this is not real. This is drawn by the artist. And one network trains the other. GANs here are a big thing. Here we have Goodfellow's original GAN paper. And then lots of paper that followed afterwards. Not like use examples, use distillation. Distillation is a trick where you take a network and you train another network to imitate what the first network does. And you can make things better and you can use smaller networks with it. That's this cluster, it's GANs. Now, here we have image super resolution as a cluster. What's the idea? I take a low-res image, but I want you to admire my photos. So I use like GAN-like things. That's why this cluster is close to it. I use GAN-like things to basically draw in the things that are outside of the resolution I have. And there's lots of applications of that. Now, where you can say private, you want to be privacy preserving. You want to like separate it around many channels that do that. So that is what this cluster does. Now, denoising. Denoising, typical application. I take a photo, there's shot noise on pixels. I want to take that out. Commercial application, it's in your phone. You take a photo at night, you will probably have seen that your photos at night are much better than before. And of course, it's much more clever. Originally, you would fix individual pixels. Now you take a little video, combine all the images, and you get really, really good images out of that. That's what's happening in this cluster. This cluster, segmentation. Related to ConvNets. But in segmentation, what I want to know is each pixel is that part of, say, one object versus another. You see where the old school solutions here. But now we use deep learning to do that, and that's why it has its own pixel, its own place. It also has a strong application in medicine. Why? If I show you an X-ray of someone who might have maybe a lung cancer or something, there's just a real big commercial field that wants to draw in, okay, I think you have a tumor there. Hugely influential on the field of neurology. And this is an area where a good number of you will later on get hired to, which is, there's this understanding in radiology. There's this understanding at radiology that the old role of a radiologist who basically looks at these images kind of says, yeah, like here's a cancer, like here's a broken bone or something like that. Those are problems that occur 100,000 times worldwide. It's pretty standardizable. A lot of radiology departments believe that it's coming as a wave at them that they can't do anything about, so they very heavily invest in it. So some radiology department have stronger deep learning groups than many computer scientists. So there's a big trend in that area. Which ones are we? Person re-identification. Big research area, of course. Take a photo of you. Maybe I'm a Secret Service or something, and then I have a camera and the airport, and it's like, yeah, same person. And you must have been traveling to New York by train. And it kind of basically track those things. I should mention one thing in this context. This is an area where people started really worrying about ethics. Because if we can use algorithms to basically identify a person where they are, it allows us to basically know things about them that traditionally we couldn't know about it, including maybe things that is compromising for them, or we can do malicious things based on this data. It's quite creepy, like there's CCTV cameras everywhere. So with these algorithms, in principle, an actor can know where we are at every point of time during day or night. And there's ethical problems about it. So this is the overall structure of the course. Now, like just as a reminder, this is the computer vision stuff, ConvNet stuff. This is what we'll cover as the first topic ever. Because this is in a way where deep learning got its feet on, where deep learning started, where like the whole field started developing techniques. Then natural language processing is an area where it had huge impact. And then reinforcement learning. Those are the three clusters that we'll basically be visiting. I told you about some 15 clusters here. Why did I tell you about it? Why did I not just say, okay, like this is like, these are the three? Well, you will run projects. And in a way, it's really sad if everyone chooses a project that's like these. This is kind of a part of research that has ended. Like we have solved by and large ImageNet object recognition. That's not where things get to be interesting. I think the things that are interesting today is if you take deep learning thinking and bring it to places where people don't do that all the time. And there's a million possibilities. And you can see that. Like this is where it started, but now we all of a sudden have like new work like everywhere in the periphery. All these clusters at the periphery are basically people saying, okay, look, deep learning gives us this wonderful toolkit. Let's take the toolkit and bring it to the various areas. We will see for a decade, probably multiple decades, a situation where a lot of commercial progress is driven by people bringing deep learning to all kinds of domains. That includes like figure out if a product is broken, figure out what I should do right now, tell me how I can be a better professor, how I can explain things better, help me understand how I could be a better violin or guitar player. There's a million possibilities that we can solve with it. And I want you to not just see these three areas. Like in these three areas, there's lots of ways how we can criticize them. Like let's also, I want you to understand the criticism. Reinforcement learning, it's just great at playing chess. If I have a robot running reinforcement learning, it can't get out of this room successfully. And so we're in this domain where it's like this wonderful, super cool research area, only that like reinforcement learning doesn't work much in the real world. Computer vision. These systems are wonderful at telling you that's a dog, that's a cat. Now, if you take a dog, you put it on top of, you throw the dog into the air. So you have a photograph of a dog, like basically jumping through the air. A lot of these systems will try and say this is a bird because there's like in the data set, there's just not very many dogs jumping through the air. So if you have a dog just on blue background, must be a bird. And so these systems kind of will wrongly identify that then as a bird. So computer vision is full of cases where if I take the data set, ImageNet, and I go outside of that domain, I take atypical images, they fail spectacular. Humans don't have any of these problems. I can show you a dog in any situation. I can show you a dog in space. You have no problem like saying, well, that's a dog. Huh? So there's a problem with like that whole computer vision literature that in a way is missing something really deep that humans have that they don't have. And similarly with natural language processing, like it doesn't lead to a real understanding. If you look at GPT-3 and we will look at related systems, they're super impressive in the sense that the text look like it's written by a human being. They are super not impressive in the sense that it looks like a human being that's entirely out of their mind, that can't keep a thought for like 10 seconds. So GPT-3, the most popular, if you want, most impressive natural language processing thing, they gave it a prompt and it asked it to continue writing. The prompt was, there's this island. There are unicorns living on that island. Most shockingly, they speak English with one another. Okay, great story. Like I can tell you all kinds of stories about like unicorns talking. The first sentence that it wrote was like, the unicorns, each of which had 2 horns on its head, did the following things. And it's like, hello, GPT-3, you don't understand unicorns, like not one bit. Why does it make those things? It doesn't understand anything about the concept of horns, of unicorns. What it understands is if there's horns involved, there's usually 2. The prior is very large that there's 2 of them. So it understands that like unicorn kind of implies that there's a horn, but it doesn't understand that it means that there's definitely only ever one involved there. And so all these areas have their problems. All these areas will ask for decades of further development to make it be really good. There will be jobs for anyone in those areas. But that means that we need to do things differently. And so as you will start thinking about projects in the coming weeks, and I will focus a lot on guiding you through how to find good projects, how to find interesting questions that are worth a project. As we get closer to that, I want you to go through this and ask yourself, what's interesting to you? Like, some of you will see yourself down there. Some of you will see yourself there. Maybe some of you will see yourself in this like old 1962 literature. Wherever you see yourself in the future, you need to have that inspiration of like seeing that overall field. Before Henrik did that visualization, I thought there's no way of showing someone how like that field looks like. No, but this is the entirety of where things are happening in deep learning. And that's why I think this is so important for you to kind of see the set of clusters, to see what these groups are. Every group here, but these are only the most cited papers. All of them are classics. I think I know more, I have read more than half of the papers that are on this. And so for all these papers, there exist thousands of other papers. And like, these are really big. These are communities. These are people that have their own conferences. And there's emerging things. Now, for example, there's now a new trend that I'm very much into, which is causal learning. How do I find out in the world that one thing affects another thing? It's surprisingly complicated. There's a surprisingly deep theory. Now there's emerging an area here where people think about it. In fact, let's see. Maybe we can even find some. There must be some. So you can put in an abstract that was a very short abstract. Look here. What do we have there? That would be the cluster at the minimum. Here. Well, fair machine learning, yes. Why do you think the fair machine learning literature cares about causality? So causality asks if one thing causes another. If I want to define fairness, now what's a good definition of fairness? It's very hard. But you can say, if I have some status, what I care about is there something about my status that causes bad outcomes? You know, like if they discriminate against me, it is because I'm a person of a certain characteristic, something bad happens to me. Whereas we want to distinguish that from, I'm a person of a certain status and something happens to me. And they might be unrelated. They might just be because of my own preferences or something. That's why there's a big field trying to combine that. Yes?
Is deep learning a rebranding of machine learning? And if not, what is the difference?
Great question, wonderful question. The first thing is deep learning is a rebranding, but not of machine learning. Deep learning is a rebranding of the field called artificial neural networks. They use the word artificial neural networks entirely indistinguishable from the way we use deep learning now. They needed a new name because neural networks were so ridiculously uncool that if you said neural networks, no one would publish your papers. So that's the first thing. Now, is deep learning a rebranding of machine learning? Absolutely not. So machine learning has lots of concepts for which you don't need neural networks. For example, support vector machines, like random forests. They're good at solving certain problems. Not only that, there's a big literature about how we deal with missing data. How do we deal with outliers? We have a good understanding of that. Deep learning inherits all of that. Now, deep learning, the use of neural networks is good in certain domains and bad in certain other domains. Where is it good? It's good in vision and it's good in language, natural language processing. And then it's good in like a smattering of small other things. What's the general property of those? Those are domains where you can get a lot of data. Now let's compare that to more classical machine learning. If I do classical machine learning, I do what's called feature engineering. I ask myself, what would be good things that would allow me to predict the things that I'm interested in? And then I have machine learning run on it. So in that sense, the human generates the features and the algorithm just chooses how to combine those features. In deep learning, we do what's called feature learning, where we can interpret the lower layers of a neural network at giving you features. This is like a learning system that learns features. So in that sense, you can say deep learning is about feature learning. And now what will we require there for that? If we want to be able to learn the features, we will generally need a lot of data. So we basically replace the human input in more traditional machine learning with like basically features that we learn from data. What that means is we'll be good in when we have a lot of data. We'll be not so good if we have little data. We will be good in domains where people have bad intuitions. We'll be bad in domains where people have good intuitions. So when it comes to, say, steering airplanes, we have like really pretty good physics for that. And deep learning is definitely not revolutionizing airline planes. And it would be a little scary given how deep learning really works. So why wouldn't it there? Because humans have very good intuition. Namely, we have physics, which give us really good simulators for that. And in other areas, like when it comes to vision, can you describe to me how you recognize a hand? No, your intuitions are really quite bad. Now you can say, yeah, your hand is kind of like bright lines here against the dark background. Well, now it's against the bright background. You can say also, like you could say, like, yeah, skin tone. Well, everyone has a different skin tone. So basically, humans have really bad intuition for how vision works. They have really bad intuition how language works. Like, how do you understand a sentence? No one can describe it. And yet, we basically, Google has like 100 million images or something. So there's any amount of data. We can learn any feature we want. We can make that easier by using knowledge that the world is translation invariant and things like that. And we use it in lots of tricks, and we will go through a lot of tricks. But no, deep learning is absolutely not a rebranding of machine learning. It is a branch of machine learning where we have reasons to believe that we can kind of meaningfully learn features. And those are the domains where it then works really well. Any other question? Yes.
Fairness, not specifically for learning. I've seen sort of like the trade-offs between, like, I guess, like accuracy and fairness. And how do you think about that? Do you think that's going to be like the end method used for doing it, or do you think there's going to be a lot of different ones that trade-offs?
There's lots of trade-offs, and we will get at some of them. Awesome. Well, I don't want to keep you here longer. Thanks for all the